Hello everyone, I would like to start this webinar session. I am Hideyuki Terashima from the University of Illinois and will be moderating this month's joint Centers webinar. This webinar provides an opportunity for Centers students to present about their research. We will have 3 presentations this session. Each presentation will be given 15 minutes and will be followed by a 5-minute Q&A session. Please feel free to ask questions anytime using the chat box feature on the GoToWebinar app. This webinar will also be recorded and posted on the drinkingwatercenters.net website after this session. Our 3 presenters today are Mariam Desfoulian from the University of British Columbia, Sarah Pope from University of New Hampshire, and Hang Dong from Lehigh University. Our first presenter is Mariam, and she will be discussing about her research on NAM removal through a combined ion exchange and biodegradation process which does not require resin regeneration. So I will be changing presenter now, and you can feel free to start when you're ready.
Yeah, thank you. Okay. So thanks and hello everyone. I'm Mariam, second-year master student at Chemical and Biological Engineering Department at UBC under supervision of Dr. Mohseni. Thanks for attending to this webinar and listening to my presentation. My presentation is about natural organic matter removal from the surface water using biological ion exchange method as a new technology in the First Nation community in northern BC. First, we'll start with a quick definition of natural organic matter. Natural organic matter, NOM or NOM, is a complex mixture of various organic substances which is made of biodegradation of animals, plants, and organic materials. And it has always been a challenge, especially for small drinking water systems. For instance, in disinfection process, it can react with chlorine and leads to formation of disinfection byproducts, which are toxic and harmful for human health. It also can affect on the quality of drinking water in terms of the color or odor, and will reduce the efficacy of the water treatment processes. For instance, it can cause membrane fouling. So there is a necessity to remove natural organic matter before any other treatments. And there are different physical and chemical methods to remove natural organic matter, such as coagulation and flocculation, activated carbon, membrane filtration, and ion exchange. Although all these processes may be used for NOM removal, their application in small communities and small systems is challenging. When we are talking about the small systems, the optimal treatment must be robust, affordable, simple, and safe to operate, use no or less chemicals, and produces low sludge or waste streams, which ion exchange filters meet most of these requirements. However, there is a potential drawback in this method. As you can see in this schematic, in ion exchange, there are chloride ions on the surface of resin. And since natural organic matter in the water is negatively charged and it has higher affinity to be absorbed to the resin surface, resin will absorb NOM on the surface and release chloride to the water. And this is the simple mechanism of ion exchange. However, after somehow resin will be exhausted and means it won't be able to absorb more NOM on it. So it needs to be regenerated, but by using a brine solution. And the spent brine solution then needs to be disposed of safely. And these put serious environmental constraints on small and remote systems that are not equipped well with the proper resources for handling and management of the spent brine. While ion exchange is a primary mechanism behind NOM removal, some other mechanisms like biodegradation resulting from microbial activity could be involved and may lead to additional degradation of NOM. Therefore, operating ion exchange system in a biological mode means no or less resin regeneration could potentially be a promising approach as it decreases the need for frequent regeneration and prolongs the life of the resin. An earlier lab-scale research in UBC as a RISO-collaborated work indicate that efficient NOM removal, like more than 50%, can be achieved in a biological ion exchange system at an extended time to a breakthrough. And a pilot study in Montreal confirmed this performance as well. Therefore, the aim of the present study was to further explore the efficacy of the biological ion exchange process at removing natural organic matter under a field condition at a pilot scale. And the case study is the surface water in Middle River Village related to the Tlaston First Nation community. And this area has its own simple water treatment system, and the community has lived with a boil water advisory for nearly a decade. The current water treatment system in Middle River consists of the filtration process as a pre-treatment to remove larger particles from the raw water and chlorine disinfection as the main disinfection process. Here we have some source water characteristics such as dissolved organic carbon or DOC, which representing NOM concentration and is around 5 milligram per liter, and pH, alkalinity, turbidity, UV absorbance of 254, and some present anions in the water such as chloride, sulfate, and nitrate. And this photo is related to the building that I installed my setup there. So we designed two same packed bed columns which are operating at a total empty bed contact time of 30 minutes and the filtration velocity of 1 meter per hour. And this schematic demonstrates the column which is 1 meter tall and half of it is filled with the ion exchange resin. 3 different sampling valves are available for taking samples in 3 different residence times or empty bed contact times like 7.5, 15, and 30 minutes. Water will be pumped from the top of the column, and with the gravity force, it will pass through the resin bed and will be treated. We also designed some valves for doing backwash the system. And this is my experimental setup, consists of 2 same packed bed ion exchange columns, which are operating in the same conditions and in parallel. And you can see the sampling valves here. These 3 pictures shows the performance of the filter bed over time, after 2 days of operation, 31 and 94 days of operation. And as you can see, during time while treating water, the color of the resin is changed from kind of white to the yellowish brown and then black. When we are talking about ion exchange, utilities usually use the term of the bed volumes, BV, which means the amount of the treated water to the amount of the resin. So for instance, for a specific amount of the resin, higher bed volumes means higher treated water. And as you can see here, we have 100 bed volume, 1500 and 4500 bed volumes during time. Going further, and after more than 200 days of operation, the columns look like this. And as you can see, the color of the whole resin bed is completely changed. Going through the results quickly, this figure shows the concentration of dissolved organic carbons representing NOM concentration in the inlet water, the blue points, and outlet water, the green points, and versus time. Since 2 columns were performing identical, results are shown as an average. Results in the outlet are shown as an average with the defined error bars for each set of data. And as expected, the concentration of DOC in the outlet was initially very low, then gradually increased to just under 2 ppm. And after saturation of the resin, followed by fluctuating around 2 ppm. And this leveling of the outlet concentration with time is likely an indication of microbial activities and the fact that the system is indeed biological ion exchange. To certify this, we looked for chloride release concentration. In this figure, we have chloride concentration versus the time for both inlet, the blue points, and outlets of the columns, the green points. We know that a purely ion exchange mechanism relies on the chloride rhythm. And as you can see, after around 60 days of operation, there is no chloride release at this point. So what it tells us is that there are some biological activities or other mechanisms during this period that are responsible for NOM removal at this stage. And in this figure, we have both dissolved organic carbon removals and chloride release versus time for both inlet and outlet waters. So no chloride release at this point is an evidence of resin exhaustion and suggesting that DOC removal at this stage might be because of the microbial biodegradation. As I told you before, there is a sulfate in source water, and sulfate is an anion with a higher affinity than NaOH to the resin. And therefore, we should have some sulfate removal in at least in initial stages of this experiment. And this figure is showing the concentration of sulfate in both inlet, the blue points, and outlet waters. And the results in effluent are shown as an average of the results for both columns with the defined error bars. As you can see, this graph can be separated in two different parts. So the first part, which is less than 160 days, in the first part, we will see a removal of sulfate of around 90%. However, for the second part, not only there is no removal of sulfate, but also we observed some release of sulfate, which is interesting, and we need to investigate more. We also measured UV absorbance for both inlet and outlet of the system at 254 nanometer. Observing the results, we can conclude that the system has an excellent performance in terms of the removal of UV absorbing compounds and organics. And converting UV absorbance to UV transmittance, we have an increase of UV transmittance from 70% in the influent to between 90 and 97% in the effluent. This is very significant because achieving a high UV transmittance will improve the efficacy of the UV disinfection process and reduces the energy cost associated with the application of UV. And ATP test has been done to study the biofilm regrowth on the surface of the resin. So 4 samples have been taken from each column before and after backwash, the blue points and the green points, and samples were taken from different depths of the filter. So 0.25%, 0%, 25%, 50, and 100%, which representing different retention times. So 0 minutes, 7.5 minutes, 15, and 30 minutes. And the data points, each data point corresponds to the average of column 1 and column 2, and the error bars corresponds to the mean and max values. As expected, we observed a profile of higher concentration at the top of the column to the lower concentration at the bottom before the backwash. However, after backwash, ATP is more evenly distributed. And comparing these numbers with the previous biological ion exchange data and biological activated carbon data that have been studied at UBC before, the filter are well biologically active at around around 7,000 bit volume at this stage. And another ATP test at a higher bit volume, like more than 13,000 bit volume, the same as previous samples, samples were taken at different depths of the reactor, 0%, 25%, 50, and 100%, like 0, 7.5 minutes, 15 minutes, and 30 minutes. And except for the top of the filter, before backwash, the concentration of microorganism for before backwash, the blue points, and after backwash, the green points, for all the depths or the different depths of the reactor are roughly the same. And here we have the results of the trihalomethanes formation potential as a disinfection byproduct. And the figure shows the concentration of THM in 5 different samples, influent, and for both columns at 2 different empty bed contact time, column 1 and column 2 at 30 minutes and 7.5 minutes. and the results confirmed good performance on THM removal. So THM levels in biological ion exchange treated water is around 200 micrograms per liter, lower than the source water, if we see the difference here. And a quick conclusion that I can mention here is that the high natural organic matter removal was observed even after resin exhaustion, and after around 280 days of operation, natural organic matter removal is still more than 60%, and sulfate release was observed after 160 days, which needs to be investigated more. And ATP test data shows that filters were biologically active, and THM formation in bi-extruded water was significantly lower than that in the influent. And at the end, I would like to thank all the people that helped me to study this pilot, and thank you all to listening to me, and I'm happy to take any question. Thanks.
Thank you, Miriam. When you were doing your tests or your research, and when you were backwashing the resin, were you using a conventional brine solution, or did you have to use something special, since not to disturb the biological process?
Okay. Actually, I'm using the conventional resin. I'm using Purolite A8060, which is a strong base anionic ion exchange resin. The only difference is that we didn't do regeneration, so we allow microorganisms to grow on the surface of resin, so we have biological mode of this system. But about the backwashing, I can go to that slide. Maybe here. So at first we didn't do backwash because actually the pilot is not here, and the operator there was not trained to do the backwash, so I need to do the backwash when I traveled there. And at the first 3 months, I didn't do the backwash. If you can see doing the backwash at this period, we didn't do the backwash because we were using the filtered water, but after, and we didn't see any evidence of the I don't know, any evidence of the clogging or accumulating in the columns. But after a while, we need to do the backwash. So every time that I traveled there, I did a backwash, if you can say.
Yep.
Did I answer your question?
Yep. Okay. Let's see. What do you think caused the change in sulfate removal after 160 days?
Actually, it was expecting, because after a while the concentration of the sulfate on the surface of the resin will be so high because it's removing sulfate and it's absorbing sulfate. And during the mass transfer rules, when the concentration of sulfate on the surface of the resin is higher than the concentration of sulfate in the source water, resin will release sulfate. But we need to investigate more that what happened at that stage that suddenly it will. And we had some Christmas break at this point. So unfortunately, I don't know what happened during these 10 days or more. So I should investigate more.
All right, great.
But it was expecting that we should have some release of sulfate at some point.
Great. It looks like that's all the questions we have for now. For everyone else that's listening, feel free to, if you have any more questions for Miriam while we're doing the other presenters, feel free to ask those questions at the end. We can go over all those questions. So at this point, Miriam, thank you for your presentation. Would you mind switching presenter to Sarah?
Sure. Thanks all.
Our second presenter is Sarah Pope, and she will be discussing her research on CO2 removals by pressurized inline diffuse aeration systems.
Hi, Thank you everyone for listening today. I am a second-year master's student at the University of New Hampshire, and as you just mentioned, I'm going to be talking about the effect of pressure on the removal of carbon dioxide. So today for my talk, I will just go through the steps of the research I've been involved in, and as an overview, I'll be talking about the actual identification of the problem, and then my research objective, and then the experimental approach, and then the data collection and analysis to date. So the basic problem is just that that significant levels of carbon dioxide in water can cause problems in piping systems. So how does the carbon dioxide get into the groundwater to begin with? It can happen through microbial respiration or the oxidation of organic.
Oh, Sarah, it looks like your mic cut out. Can you still hear us, Sarah?
Okay, I think the audio connection was restored. I'm not sure what happened.
No problem.
Okay, anyway, and so again, the last thing I mentioned was that the carbon dioxide can percolate down through the soil, or there can be acidic groundwater plumes that could just have been a result of anthropogenic activities such as mining. So once the carbon dioxide is in the water, it reacts with the water itself, and this creates a dynamic system that can result in several species. And the levels of these species are constantly in flux, but the two that are of concern in water systems are H2CO3, which is carbonic acid, and the carbonate ion. And the reason that the carbonic acid is a problem is because it's corrosive. And these pictures show some examples of corrosion that has occurred because of carbonic acid in piping systems. Another time that the carbon dioxide is a problem is when the carbonate ion is present. And a common place this can occur as far as problematic issues go is when groundwater containing carbon dioxide or the carbonate ion meets surface waters, which may contain other species that can combine with the carbonate ion and will see precipitates. And these pipes show examples of that. It could be magnesium carbonate or calcium carbonate. And as you can see, the sediment, the precipitate there seriously compromises the functionality of the pipes. So to prevent these problems, the solution would be to lower the carbon dioxide level in the pipes. One way to do that would be to depressurize the system. And that would simply allow the water to have contact with the atmosphere, and the volatile carbon dioxide would then transfer to the gas phase. However, another way would be to attempt to do the removal under pressure. This would allow a system to maintain its pressure. There would be a smaller treatment footprint, and we could treat localized areas of concern. So that leads to my research objective, which was simply to investigate the effect of pressure on carbon dioxide removal from water using air stripping, and to hopefully use this to contribute to innovative water treatment technology. So the experimental approach was first to design an experimental procedure, then conduct pilot testing to collect data, and determine values for the constant governing the aqueous and gas phases of carbon dioxide, and last, to develop and verify a model to predict carbon dioxide removal in a pressurized system. The plan for the pilot testing was to perform diffused aeration or stripping on water with high levels of carbon dioxide. Also, the aeration would be performed at various pressures. So this is a picture of the equipment that we constructed to be used for the diffused aeration pilot testing. And I'll just point out the features of it. The vessel itself held approximately 2.6 liters. At the bottom here is an inlet for the carbon dioxide gas to create an initial high dose in the water. There is also an air inlet at the bottom for the stripping process. And this is the aeration stone that created the diffused air. There is a sampling port at the bottom to take water samples. At the top is an airflow meter, which also served as the air outlet. There is another air inlet so that the system could be pressurized before a batch was begun if necessary. And the vessel itself had a pressure threshold of approximately 70 psi. So the first phase of the research were batch runs. The experiments were batch runs, and the general procedure went through these steps. First, an initial batch of water was created with a significant level of carbon dioxide. The vessel was filled with approximately 2.4 liters and then dosed with the carbon dioxide from a supply tank. After the initial batch was created, 2 initial concentration samples were taken. The initial pH was measured and recorded. If necessary, the system was pressurized. Then I would begin the airflow and adjust it with the air, with a regulator and an airflow meter. And once the airflow and the pressures were steady, I ran the batch for the determined length of time. I tried to minimize this adjustment time so that it didn't actually affect the results of the batch. After the proper length of time had been run, the airflow was turned off, the vessel was slowly drained into a container. Samples were collected by withdrawing liquid from below the water level. The final pH was measured and recorded, and then the vessel was rinsed with RO water prior to the next run. Developing the sampling procedure and finding a way to analyze the carbon dioxide content of the water was actually quite a bottleneck in the startup of the project. It was difficult to find a way to determine the aqueous phase concentration of carbon dioxide. So in the end, we decided on an indirect method, and this utilized Henry's law, which provides a relationship between the gas phase and aqueous phase concentrations of a solute. In this case, the carbon dioxide was the solute. And in the equation, you can see Hcc represents the Henry's law constant, and it is a known value at atmospheric pressures. And so if you know the carbon dioxide concentration in the gas phase, the concentration in the aqueous phase can be calculated. So a water sample was collected in a jar with headspace, and after allowing time for the sample to reach equilibrium, the air concentration was measured, and Henry's law was used to back calculate the aqueous phase concentration of the carbon dioxide. These are the jars that the water samples were collected in. They are 60 milliliter jars with a septum. And so the water samples were put into the jars with the lid immediately affixed just to minimize CO2 loss. Then I gently and repetitively inverted the jar to facilitate equilibrium of the gas and water phases in the jar. And then I would analyze the samples on the day of collection using this instrument, which is a LICOR gas analytical instrument. Using a needle and syringe, 5 milliliters of air was withdrawn from the jar through the septum, and this sample was then injected into the tubing circuit of this machine, and this process was repeated for each sample. The reason we chose that was also partially because we had access to the machine already on campus, and it was a very effective way to measure carbon dioxide in the gas phase. So once the raw data was collected, we could use the calibration curve from known standards that had also been measured, and then the relationship could be used to determine a carbon dioxide concentration for the air phase of each sample. And then once we had the air phase concentration for each sample, the aqueous phase concentration, which is what we really needed, could be calculated using the Henry's Law relationship. This is an example. This is a chart showing the different runs that were performed. There were 3 different air to water ratios that I investigated and different pressures as well. So as you can see, for an air to water ratio of 2, I did batch runs at atmospheric pressure, 20 psi, 35, 50, and 70 psi. And this is an example of the results from a batch run. In this case, 4 runs were done for the setting of a pressure of 20 psi and an air to water ratio of 5. So in this case, it was good to see that the initial concentrations were in agreement and the final concentrations were agreement, and this seemed to be the same for each run. Also, the percent removals that I got for all 4 runs at this setting were pretty close in agreement as well. So the compiled results of all the batch runs are shown in this graph, and each line is a different air to water ratio. The bottom is the air to water ratio of 2, the middle orange is an air to water ratio of 5, and the top blue is an air to water ratio of 10. As expected, the percent removal decreased with increasing pressure, and also the increased spacing between the lines as pressure increases shows that the effectiveness of the air to water ratios is more significant as the pressure increases. So the data that I collected could then be used to find the Henry's Law constant at different pressures. The equation shown here is an established model for the batch stripping process. Using this equation, you can find the Henry's Law constant at each pressure by plotting the natural log of the final concentration over the initial concentration as a function of time. And this should yield a linear relationship. The slope of the resulting line is a value representing, as you can see, Henry's Law constant times the gas flow rate over the volume of the batch, so that at each pressure, a value for this Henry's Law constant can be calculated. This graph shows that process I just described. And again, this top line is for pressures of 20, the middle line is for pressures of 50, and the bottom line is for pressures of 70. And the slope is reflective of the change in the Henry's Law constant. As the pressure increases, the slope is flattening out, which indicates a decreasing value for Henry's Law constant as pressure increases. This makes sense since the Henry's Law constant in the equation used with this graph is a ratio of the air phase concentration to the liquid phase concentration. So these were good results. We were seeing what we expected to see, but also from that slope we can then calculate values, as I said, for the Henry's Law constant at these different pressures. And once we have those values, the relationship between the values for pressure and the constant can be analyzed. And I hope to determine if there is a first or second order relationship between those two. Then I can find the rate constant that governs that relationship, which will then allow me to develop a model that can predict the Henry's law constant for a given pressure. This will provide a way to assess the feasibility of carbon dioxide removal at different system pressures. And we can also confirm the Henry's law constant and the model prediction with a continuous flow stripping process, which will be the last phase of experimentation for this research. So that pretty much wraps up my talk for today, and thank you for listening. Are there any questions?
Thank you, Sarah. It looks like we don't have any questions at the moment, so
Okay.
I would like to move on to our next presenter. But again, if anyone has any more questions for Sarah, we can go over those questions at the end. All right. So our final presenter today is Hang Dong, and he will be discussing his research on nitrate removal from groundwater sources through a novel anion-cation two-bed ion exchange process, which eliminates the use of brine during regeneration.
Hello, here's my presentation. Thanks for the previous two presenters. So they introduced some fundamentals about ion exchange and also carbon dioxide. So this is very helpful for my presentation. So my work is trying to combine ion exchange and the carbon dioxide by remove nitrate from groundwater and without produce the brine concentration. So the way I'm using is using carbon dioxide. Okay. So as the first presenter mentioned, traditional ion exchange technology requires, high concentration of brine to regenerate. So what they do to remove nitrate is using nitrate selective anion exchanger. So say we have the groundwater containing nitrate, go through the nitrate selective resin, and then during the removal, nitrate will go to the resin and then release chloride. While after the resin exhausted, people use high concentration of sodium chloride to regenerate the resin. So, but the regeneration process is not a 1:1 ratio, which means to kick out one nitrate from the resin, you need to use many times more concentrated chloride, which means after regeneration process, it generates spent regenerant, which we call the brine, where containing not just the nitrate we removed, but also there are many excess sodium chloride in there. So how to deal with this waste is a huge problem for this ion exchange process. So as I mentioned, the spent regenerant is going to containing sodium nitrate, which being removed from the water, and also excess sodium chloride from the regenerant. So currently there are many research ongoing to study how to deal with this waste. So some people try to using biological denitrification, which means remove the nitrate using bacteria, and then all the sodium chloride left could be used as regenerant again. And also people started to using catalytic denitrification and reuse, and also, or just, put this spent regenerant into the ground using deep well injection. So the catalytic denitrification obviously gonna consume a lot of energy, and also deep well injection is gonna be banned by more and more states because some study show that it relates to earthquake or some other environmental issues. So to avoid this spent regenerant, we are thinking about to kind of change the regeneration process by eliminate the consumption of sodium chloride. So we're gonna try to use carbon dioxide to do the regeneration. Because carbon dioxide, as Sarah mentioned, it forms carbonic acid when it dissolves into water. So carbonic acid is very special. So it could dissociate into hydrogen ion and bicarbonate. So as carbonic acid itself is like a weak acid, but when it's dissociated in the water, it forms bicarbonate, which is a weak base. So this is a very unique chemical. It could perform as both acid and base, even though it's weak. So our process is also, again, using ion exchange resins, but we are not using traditional anion exchanger. So we have invented a special resin before. We called HAIX ZR. ZR means zirconium. So we loaded some zirconium nanoparticles into the resin. So, and the parent resin is still naturally selective. So this resin gonna containing two kinds of functional groups. So the first one is the traditional functional group from the resin. So you're gonna do traditional ion exchange, which means it's gonna exchange nitrate, but instead of releasing chloride, so we put bicarbonate in the resin first. So while absorbing nitrate, it releases bicarbonate. And then another functional group is the nanoparticles, zirconium, we kind of fix into the resin. This resin could also treating other problems, say fluoride. So these zirconium oxide nanoparticles, they have high affinity to fluoride because sometimes fluoride is always coexist with some nitrate contaminated water. So after the first column, basically all the anions gonna become bicarbonate. So which means the effluent from the first column is became like a sodium bicarbonate, calcium bicarbonate, or magnesium bicarbonate. Sorry. Then we pass through this effluent into our cation exchanger, and this cation exchanger is loaded with hydrogen ion, and this cation exchanger gonna exchange all the sodium chloride, all the sodium and calcium into hydrogen ion. So then you could see that all the anions in the source water became bicarbonate. All the cations in the source water became hydrogen ion. So they combined together, became carbonic acid. And then further on, it became carbon dioxide and can escape from the liquid phase and became a gas. And this way, we are not just remove nitrate, and we are also achieving partial desalination, because some salts, they became carbon dioxide and being eliminated from the water source. So the resin we use as a cation exchanger, we named is SST WAC. So this resin is special because during regeneration, it's gonna help us a lot. So during regeneration, we use pressurized carbon dioxide and water. So which means we saturate the water under high pressure of carbon dioxide. Then the water it's gonna form carbonic acid solution. So during regeneration, we pass this carbonic acid solution into the second column first. And then you could see that all the hydrogen ion gonna go to the resin again and kick out all the cations being removed in previous surface cycle. So at this process, since carbonic acid is weak acid, so usually people use strong acid to do the regeneration because they provide a high concentration of hydrogen ion. But here here the carbonic acid actually it only provides a low concentration of hydrogen ion. So our resin is a kind of special design resin because the low concentration hydrogen ion is hard to get into the middle of the resin. So if there's some cation in the middle of the resin, it's hard for the hydrogen ion to regenerate those cations. So this resin is special design. There's no functional group in the middle. So all the ions are cations being removed on the surface. So it's very easy for this to regenerate with hydrogen ion, even at low concentration. And then after the second column, the effluent is gonna containing sodium bicarbonate, calcium bicarbonate, because all the because all the hydrogen ion is already being go to the resin again. So this bicarbonate solution gonna then go to the first column to regenerate the first column. And also kick out all the nitrate being removed in the previous cycle. So and then this gonna finish the whole process. So we bring back all the both cation and anion resins into the form we desired. So cation resin with hydrogen form, hydrogen ion, anion changer with bicarbonate ion. So this is the setup we use in our lab. So you could see, sorry, I'm coughing too much. So on the left, there's a carbon dioxide cylinder, and then there we have a 10-liter tank, so containing water. And then if this tank opening to the carbon dioxide cylinder, it's gonna saturate with carbon dioxide and provide carbonic acid. So then we have a spare column, 300 ml, and also a backup tank to do the same thing as the first tank. And then the last two column is used to support our ion resins. As you can see on the right, we have the column loaded with a hyper ion exchanger with zirconium, and then this column we containing STWAC as the cation exchanger we mentioned. And then we have during the service cycle we use a pump to pump the feed water and go through the very right column and then go to the second column, then get the water back. Then we collect them to study the nitrate removal performance. And then during the regeneration cycle, we just open the water tank into the carbon dioxide cylinder, and then the carbonic acid solution gonna go through in the reverse direction to regenerate both columns. And this during the regeneration time, we don't need the pump because the pressure in the water tank itself gonna driven the water go through the whole columns and to finish the regeneration. So this is experimental data we studied for the nitrate removal performance. You could see that while feeding water with say 60 ppm nitrate, so we could consistently remove nitrate for almost 200 bed volumes. And you maybe could realize that in the beginning, there will be some around 20 ppm of nitrate leakage. So this is very common for all the nitrate removal industry, because nitrate is very hard to be regenerated, and it's different, especially for nitrate selective resin, because nitrate selective resin prefer nitrate very much. So during regeneration, it's gonna be very difficult to completely regenerate. So for the economical view, to completely regenerate the nitrate is not necessary, because as long as the nitrate is below the standard, we could just achieve our goal for nitrate removal. So we kind of finish 3 cycles of nitrate removal run with the real groundwater from Lancaster, Pennsylvania. So their nitrate level is lower than what we tested here, because we, after got the water, we spike some more nitrate to study like a little bit higher concentration of nitrate, how our system gonna perform. And then this is the regeneration cycle. This data is like previously we used only pure carbon dioxide. You could see that because even for using high concentration of brine, it's hard to regenerate the nitrate. So with low concentration of carbonic acid solution, is even more difficult. So you could see that the green one is for sulfate, the red one is for chloride regeneration. They are very efficient and could be complete within 25 bed volumes, or further, or even 20 bed volumes could finish like 80% of recovery regeneration. But the blue one is the nitrate. You could see is very different from the sulfate chloride, because nitrate is hard to be regenerated. So if you want to do fully complete regeneration is going to consume a lot of regenerant. So this is kind of a challenge in the beginning, and then we modify this process. So we decide to use 20 bed volumes of or 30 bed volume of the carbonic acid solution, and then we use 1 bed volume of sodium bicarbonate to do the regeneration. But so even we still bring in some very small amount of salt. But this is still like we eliminate 80% of the salt consumption for the traditional way, traditional nitrate removal process. And as I mentioned earlier, this process is not just remove the nitrate, it's also doing partial desalination because some cations and anions are combined together, became carbon dioxide, and eliminates from the aqueous phase. You could see these 3 cycles of runs, and this is the conductivity data, which means the could easily convert to TDS. You could see the around 200 bed volumes. It is still removing the doing the partial desalination. So yeah, the reason as I mentioned is because cation and anions became carbonic acid and became carbon dioxide and eliminated from the aqueous phase. And you could see for the sample we collected, there's a lot of bubbling there. This is carbon dioxide eliminates escape from the aqueous phase, and then the aqueous phase became partially desalinated. And that's all my presentation, and thanks. So any questions?
Thank you, Hang. It doesn't look like we have any questions at the moment. Can give it a few seconds. But just for everyone else, once again, that this recording will be posted on the Drinking Water Centers.net website, and you can find the abstracts for each presenter there as well. So if you have any questions later on, you can get the contact information from there as well.
Okay, sure.
Yeah. Well, I guess at this point, I would like to conclude this webinar. I would like to thank all our presenters today, and I hope everyone has a nice day. Thank you.